Okay, so today we shall discuss about the RSA crypto system. We will continue with the RSA crypto system, and what we shall discuss is about how to factor the public modulus. Okay, so therefore this is a quite big topic, but what we will shall discuss is about some commonly known techniques to do so. Okay, so essentially we shall be discussing about three main algorithms. One is called the Pollard p minus 1 algorithm, and the other one is called Pollard row algorithm. And then we will conclude with another algorithm which is a random squares algorithm. It is called Dixon's random squares algorithm. Okay. So, some basic points about factoring algorithms. So, most obvious way to attack the RSA would be to try to factor the public modulus. So, what we have discussed is that if we are able to factor the public modulus of RSA, then we shall be able to compute P and Q, right, because n is a product of two prime numbers P and Q. And if we know how to factor, then we will know the value of P and Q. So, if we know P and Q, then from there we will be able to ascertain the value of phi n also, the Euler-Toshan function, right. So, if coefficient. So, therefore, if we know what is phi n, then from the from the encryption exponent we shall be also able to compute the decryption exponent, right. So, therefore, after that RSA security is compromised, right. So, this is the most obvious way of attacking an RSA algorithm. So, therefore, we shall study about some commonly known algorithms, but the modern algorithms are some sieving techniques like quadratic sieve, elliptic curve factoring sieve and number field sieve, but we will really not go in depth in these sieving techniques, but what we will essentially discuss about is about something which are also very important algorithms, but maybe you can think as these algorithms are something like precursors to these algorithms. Okay. So, what we shall discuss is about P minus 1 Pollard algorithm, so which is a P minus 1 factoring algorithms. So, in this algorithm we shall try to factor P minus 1, okay, and because you know that if P is a prime, then P minus 1 is an even number, it is a composite number, right. So, we shall it is based upon the factorization of P minus 1, and the other very interesting algorithm is called Pollard's row algorithm, and it is yet another application of the birthday paradox to cryptanalysis. Okay. So, of course, we have the trial division algorithm, but you know that trial division is not very efficient when the sizes become large. Okay. So, we know that a complexity of a trial division is works like this. If n is composite, then n has a prime factor which is less than square root of n. So, if your n is typically less than 2 power of 40, this is quite okay. Okay. But the thing is that if your n becomes larger, then you need to do something better than the ordinary trial division technique. Okay. So, we shall study about two algorithms. So, in this case note that what we are searching is for non-trivial factors of n. Okay. So, which means that we are not really going to the prime factorizations. Okay. So, because what we will study, and if we are able to do this, then using our previous primality tests which we discussed, and there are many more actually, we can ascertain whether a number is prime or not with some reasonably high probability. If it is not prime number, then we shall again use the same technique, right. So, therefore, we can again and again apply these factoring algorithms and we can factor. Okay. But in this discussion, rather in today's discussion, we shall be concentrating on finding out non-trivial devices or non-trivial factors. So, non-trivial means of course not itself and not 1. Okay. So, excluding them, we shall be trying to find out or compute the corresponding factors. Okay. So, the Pollard's factoring algorithm is based upon the factorization of P minus 1. Okay. So, concentrate on this, that is if P minus 1, so you remember that P is a prime number, right. So, therefore, P minus 1 is a composite number, right. So, if P minus 1 is a composite number, then we shall be able to factor out P minus 1. So, therefore, P minus 1 can be factored in terms of prime factors. Okay. So, you see that P minus 1 will be in that case equal to q1 to the power of e1, q2 to the power of e2, and this is not k. Okay. So, this is again another problem with the software. So, it is q1 to the power of e1, q2 to the power of e2 and so on. Okay. So, it works like this. It is q1 to the power of e1, q2 to the power of e2 and so on. So, consider there are k distinct prime factors. Okay. So, now here you I mean for this p minus 1 algorithm discovered by Pollard, actually you need a bound. Okay. So, this bound is denoted by say b. So, how is that bound chosen? I mean although we do not really know these factors, but the assumption is that suppose I know a fact, that is all these prime powers which divides p minus 1 are lesser than or equal to p. Okay. So, suppose we know this fact. So, what does it mean? That is all these prime powers like say q1 to the power of e1, q2 to the power of e2. So, for example, if I arrange them like this, like if I know that okay, that these are all, I mean without loss of generality I can do such kind of ordering, right. So, what I can assume is that all these prime powers are less than equal to b. Okay. Suppose I do not know these prime powers, but I know that there is a bound like this. Okay. So, from this we know that all these prime powers. So, if I consider the series of b factorial, okay. So, what is b factorial? B factorial is b into b minus 1, b minus 2 and so on till 1. Okay. So, you note that because of this particular assumption in these terms like b, b minus 1, b minus 2 and so on, these terms like q1 to the power of e1 or q2 to the power of e2 or qk to the power of ek must have occurred at least once, right, because these are distinct primes, right. So, they are not equal, that is you will not find out two powers which will match, right. So, all of them will be distinct terms. So, in this series they must appear somewhere, right. So, what does it mean? It means that p minus 1 actually divides b factorial. Right? Is this clear to us? Because p minus 1 is nothing but these powers, right. So, if these powers are there in b minus 1 factorial somewhere, so therefore, this particular term must have divided b factorial, right. So, this is the basic observation, that is if you know that there is a bound like this, then you know that p minus 1 will divide the factorial of p. Okay. Right. So, now you see that what we are essentially doing in this algorithm, okay, is like this, that is you see that for you start like this, that is you just assume that a is equal to 2 and then what you do is that you start from 2 to b and you compute a power j mod n. So, what are you essentially doing at the end of the for loop? You see that first of all you have got a j equal to 2, then you have got j equal to 3, then you have got j equal to 4 and so on. So, what are you computing? A to the power of b factorial, right. So, at the end of the for loop you have got a is equal to a to the power of b factorial, right, and modulo n, right. So, at the end of the for loop what you essentially have is, so at the end of the for loop okay, you have got a is equal to a to the power of b factorial mod of n. Okay. So, now you observe another property which says that at the end of the for loop, so therefore, you have got a equal to a congruent to a to the 2 to the power of b factorial, because you started with a equal to 2, right. So, therefore, I can say that a is equal to 2 to the power of b factorial mod n. Okay. So, now you see that I can write from here that a is equal to, because of this I can write a equal to k n plus 2 to the power of b factorial, right, because if I divide by n then 2 to the power of b factorial is a remainder, right. So, what is n? N is p into q, product of two prime numbers. Okay. So, plus 2 to the power of b factorial. Okay. So, now if I take a modulo p, then I can write that a equal to 2 to the power of b factorial mod of p, right. So, from Fermat's little theorem we know that a to the power of p minus 1 is equal to 1 modulo p, and we also know, or rather since p minus 1 divides b factorial, then this implies that a which is equal to 2 to the power of b factorial modulo p is actually equal to 1 mod p, right, because b factorial divides p minus 1, or rather sorry p minus 1 divides b factorial, right, and we know that 2 power of p minus 1 is equal to 1, and therefore 2 to the power of p minus 1 some multiple will also be 1. Do you follow this? So therefore, no, what I am saying is this, that is p minus 1 divides b factorial, right. So therefore, b factorial is some constant times p minus 1, right, and therefore if 2 to the power of for any a, right. So therefore, if 2 to the power of p minus 1 is equal to 1 mod p, then 2 to the power of p minus 1 into that constant will also be equal to 1. So that means 2 to the power of b factorial is equal to 1, right. So therefore, from here we know that p divides a minus 1, correct, but you know that p divides n also, right. So therefore, which means that if you compute the GCD of, so therefore you know that p divides a minus 1 and p divides n. So therefore, if a is not equal to 1, then the GCD of a minus 1 and n will give me one non-trivial factor of p of n, right. So that means the GCD of a minus 1 and n should give me one non-trivial factor of n, but if a equal to 1, then that means that this gives a failure, this algorithm fails, okay. So which means that for you have to again start with another bound b, right. So therefore this is actually how the algorithm works, and we can see some examples for that. So for example, if you come to this example, then n equal to 157707084441, so it is relatively a quite good number. So therefore if you set a b equal to 180, so you know see that this setting of b equal to 180 is arbitrary actually, okay. So what is the assumption, that all the factors which are there actually, all the prime powers must be less than or equal to 180, okay. So if that be so, then you say that here in this case if you do this a equal to 2 to the power of b factorial modulo n, then actually after the end of the for loop you get a value of like this, okay. Example, we shall continue with this example. So therefore n is equal to 157707084441 is the number which we have to factor, okay. So you see that what we have done here is that we have set a value of b equal to 180. So what is the assumption, that all the prime powers of n are essentially less than equal to 180. So therefore this is again an assumption, right. So we start with some assumption, and if I do this computation of 2 to the power of b factorial mod n, then a becomes, after the end of the for loop, it becomes equal to this particular value, okay. So now let us compute d, which is the GCD of a minus 1 and n. So you see that a in this case is not equal to 1, okay, mod of what you have seen, right. So therefore in this case if I consider or compute the value of GCD of a minus 1 comma n, then I get 135979, which is indeed a factor of this number, okay. So you see that this particular technique actually relies upon largely upon the value of 180, that if 180 is properly chosen or not, this bound is properly chosen or not. And you see that if this bound is large, like for example if I make the bound very large, okay, then this algorithm is guaranteed to succeed, okay. But if this value of b is small than the actual value, then this algorithm will fail, okay. So which means that you see that if this b is very large, like if I set the value of b to be very large, then although the algorithm will succeed, but actually your number of computations will also increase, okay. So it will very slowly it will go to the trial division algorithm, okay. But if the value of b is indeed small, then this algorithm will succeed. So which means what, that in order to stop this factorization by this particular technique, you need to ensure that p minus 1 has also got large factors. Okay. So, that means if p minus 1 has got all these factors very small, then the Pollard p minus 1 algorithm will be engaged to break or factor the value of n. Okay. So, which means that you see that there are some finite points here, that there are b minus 1 modular exponentiations. So, you see that what we have done is that in that for loop we have computed all these modular exponentiations, and you remember from the square and multiply algorithm which we engaged to compute the exponentiation, there are actually around 2 log b modular multiplications. So, I have accounted taken into account the multiplication as well as the squaring operation. Okay. Now, the GCD can be computed in O log n whole cube using the Euclidean algorithm, and therefore, the overall complexity is like this, like something like b log n square, because multiplication takes log n square plus log n cube. Okay. And therefore, if you make your b to be something like log n or logarithm in n, then actually you have a polynomial time algorithm to solve this problem. Okay. So, but the thing is that if this value of b is large and if it is of the order of n itself, then this algorithm will not be so useful. Okay. So, which means that however, if b increases, then the success probability increases, but the algorithm becomes as slow as the trial division algorithm. So, therefore, the modulus n should be such that p minus 1 does not have all prime powered small. So, this is our observation. So, if you want to implement or choose RSA parameters, then this is also another criteria that we should keep in mind, that is p minus 1 should not have all prime powers which are small, should have at least one large prime power, right. So, that is the observation that we obtained from the Pollard p minus 1 algorithm. Okay, that is the lesson we learned from p minus 1 algorithm. So, this is the description of the Pollard p minus 1 algorithm. So, Pollard gave yet another nice algorithm which is called the Pollard's row algorithm. Okay. So, any doubts till this point? So, Pollard row algorithm works like this. Suppose you have been given some value of n, which I say assume to be say 7171, and the question is what is a value of p which will divide the value of n. Okay. And this is a very interesting algorithm. You see that we know that p must be lesser than or equal to square root of n. Okay. So, we know that. So, therefore, a possible method could be like this, like you randomly choose 2 points a and b, okay, and you find out modulo p. So, if your p is a small number, then there is a very large chance that a and b will be congruent to each other modulo p, right. So, what does it mean? P divides a minus b, okay, and we also know p divides n. So, that means if I compute the GCD of a minus b and n, then I should be able to get one non-trivial factor, right. So, that is the basic point. So, therefore, now therefore, GCD of a minus b comma n indeed gives us a non-trivial factor of n, and from Birthday paradox, if the number of elements which I choose is of the order of say around square root of p, then we have got a large chance of a collision. Okay. So, you have got distinct points, say p distinct points, and from there if you choose if you choose square root of p elements randomly, then from Birthday paradox we know that there is a high probability that both the elements will actually collide, right, and therefore, this technique should work. Okay. So, but the thing, so this is a basic principle behind the Pollard's row technique. Okay. But there are some pitfalls in this straightforward application. What is the pitfall? That is, from p points, if I choose all possible points, then what can be in the worst case the number of points? It will be say pc2, right. That is, if I choose p points, from there I have to choose all pairs, all possible pairs, and find out which pair satisfies the relation of, I mean, see, one thing you have to keep in mind, that you do not know the value of p, right. So, you do not know, you will not be able to check this condition that a and b are congruent to each other modulo p. Okay. So, what you will do is that you will compute the GCD of a minus b and n and see whether you get a non-trivial value. Okay. You do not have a handle over p because you do not know p, right. So, what you can do is that you can randomly pick two numbers a and b and compute the GCD of a minus b comma n, okay, and hope that it is a non-trivial factor. So, what we are giving you guarantee from the Birthday paradox is that if a and b are congruent to each other modulo p, then this should give you a non-trivial factor. okay, and if the number of points you choose are of the order of square root of p, then you have a large probability of such an occurrence, right. There is a significant probability of this particular occurrence, but the point is that if I give you, for example, square root of p points, even from there how many possible pairs can you have? There can be square root of p C2 possible pairs. So, square root of p C2, what is the order? It is p, and what is the order of p? It is square root of n, right. So, therefore, you still have the efficiency same as that of the trial division algorithm, right. So, which means you have to reduce the number of GCD computations. The number of GCD computations by this straightforward method is still quite high. Okay, you understand. So, therefore, what I am saying is this, that is, if I pick say A and B and I compute the GCD of A comma B, I choose another value of say C, and then I need to compute the GCD of A comma C, GCD of B comma C, and so on. Again you pick up B, you have to compute the GCD of D and A, GCD of D comma B, GCD of D comma C, and so on. Okay. So, you see that if the size that you choose from is of order of square root of p, why? Because if the order is square root of p, then you have a large probability that at least you will get two colliding A and B, right. You will get one pair of colliding A and B. Okay. But then the number of choosings that you are doing is or rather number of GCD computations you are doing is still of the order of p, okay, because you are doing square, I mean it is xc2, right. So, therefore, the order is still p, and that means the order is still square root of n. So, which means that the algorithm is no better than the trial division algorithm till now. Okay, the memory is still overrooted, time is also still overrooted, right. So, therefore, we need to do something better than this. Okay. So, there are some improvements that we will discuss. Okay. So, therefore, the main objective is that we have a fairly good idea to find out the factors, but what we need to do is still to compute less GCDs and do our job. Okay. So, in order to do so, what we do is this, that is, we choose a polynomial fx which is equal to x square plus a. Okay. So, this is some random polynomial that we have chosen. So, fx is equal to x square plus a to randomly choose the numbers modulo n. So, what we do is that we choose the number x modulo n and compute fx equal to x square plus a modulo n. So, therefore, the idea is that this should be giving me a random next number actually. So, therefore, I am engaging this polynomial to give my random numbers. Okay. So, therefore, I give a seed value of x, I get x square plus a, I again make that x and again apply it. So, I keep on applying the same fx again and again. Okay. So, you note that there are some restrictions here, that a cannot be equal to 0 or minus 2 modulo n. Why? Because if fx equal to x square only, then there is a problem. What is the problem? That there can be some fixed points, like for example, if I choose fx, I mean x equal to 0, right, then it gets stuck at 0. Okay. Similarly, if you choose x equal to 1, it is still stuck at 1. Okay. And if it is minus 2, then there is another stuck at point, then it is minus 1. So, minus 1 square plus, so if I if you make the value of x equal to 1, then it is 1 square minus 2, which means it is minus 1. So, if you feed minus 1, you get minus 1 square means 1 minus 2, so that is still minus 1, right. So, therefore, we shall actually avoid the value of a equal to 0 or minus 2. Okay. So, we will just maybe you can just choose fx equal to x square plus 1, it is a very simple function, right. So, the main idea of the Pollard row algorithm is like this. Okay. So, suppose you choose xi and xj which are same modulo p. Okay. So, what we will prove from here is that in that case, if rather we know that if xi and xj are same modulo p, then fxi and fxj are also same modulo p. Okay, because f is actually a polynomial in all integer coefficients. Okay, so therefore you have got, if you apply, you know that this is a standard result, right. So therefore I know that fxi and fxj which will also be congruent to each other modulo p. Okay. So, now you say that suppose I need to compute xi plus 1, okay, and if xi plus 1 is congruent to say fxi mod n. So, that is the next computation, right. So, you plug in xi and I compute xi plus 1 which is congruent to fx, I mean which is actually equal to fxi mod n. So, this is the next computation of the function of f. Okay. So, fxi mod n, okay, will be equal to, so we have got xi plus 1, so we have got this result, that is xi plus 1 mod p, okay, we have got xi plus 1 mod p equal to fxi mod n mod p, and that is equal to fxi mod p. Why? Because xi plus 1 mod p, so therefore what I am saying is that you have taken xi plus 1 is equal to fxi mod n. Okay. So, what you do is that you compute a mod p on both sides. Okay. So, if you do a mod p on both sides, then what does happen? Okay. So, what I am saying is this, that is suppose you have got this result xi plus 1 which is equal to fxi mod n. What we do is this, that is I compute xi plus 1 modulo p. Okay. So, this should be equal to fxi modulo p. Why? I have proved this actually similar thing in the Pollard p minus 1 algorithm. It is a straightforward thing. So, I mean there is nothing to prove actually. So, therefore, xi plus 1 mod p is congruent to fxi mod p. Okay. So, from this actually we know that fxi mod p is actually congruent to fxj mod p, right. So, therefore, I can write here that this is nothing but fxj modulo p, correct. So, therefore, fxj mod p, okay, is equal to from, so therefore, what we are essentially trying to say is that xi plus 1 will also be equal to xj plus 1 modulo p, right. So, therefore, if xi, I mean if you get xi which is congruent to xj mod p, then actually using this computation of f, I mean this is the next modulo n computation, then from there you can say that xi plus 1 will also be equal congruent to xj plus 1 mod p, right. Do all of you see that? Yes. So, that is all obvious, right. So, therefore, now we can say from here that xi plus delta will actually be congruent to xj plus delta modulo p. Okay. I can vary the delta. So, therefore, I can say that okay, delta is for, that is for all delta which is greater than 0. This is true. So, what does it mean? It means that if you find two such values xi and xj which are same, then after that, and because after this collision all the values in modulo p are actually locked with each other. Okay. So, therefore, you can imagine that this particular relation gives you that okay, if I just randomly choose some points, okay, then you will find that if, so therefore, if I plot them, like if I just start to note this number, so I get for example xi, okay, I get the next number, I get the next number, I get the next number and so on. So, you keep on getting some numbers which are distinct actually. Okay. So, after some point if you keep on continuing like this, you will find some value for which this xi and xj will become equal to each other, right. So, that means basically you get a letter like a row. So, that is the idea why it is called a Pollard's row algorithm. Okay. It looks like the Greek letter rho actually. So, after that actually all these computations will give you the same result, right. So, you have a tail part here and after that there is a circular part. Okay. So, that is the reason why it is called a Pollard's row algorithm. Okay. So, therefore, again it will look like, so this is an example from Codman which says that if you choose for example mod 1387, you see that you get some row like this. If you take modulo 19, you get a row which looks like this is a smaller row. If you take mod 73, you get a row which looks like this. Okay. So therefore, what the idea is that whatever you say, that whatever modulo you take, after some value there is, if you just randomly choose some points, you are quite expected to get a collision, and once you get a collision, after that this follows, right. So therefore, xi plus 1 will be equal to xj plus 1, xi plus 2 will be equal to xj plus 2 modulo p. Okay. So therefore, you will always get a lock like this. Okay. So it will be xi plus 1. So therefore, you see that in this case maybe it is not so clear from the diagram. Okay. You will find that if there is a lock here, then after some time you get a 6 here. So you get a, so I will spell out the numbers. It's say I start with 2, the next number is 3, the next number is 8, the next number is 6, the next number is 16. After that you again get an 8. That means that it keeps on colliding. So therefore, in the sequence actually there are 2 colliding numbers, and after that it keeps on colliding in this fashion. Okay. So now our goal is to find out 2 such terms for which xi and xj are congruent to each other modulo p. Okay. And what we have seen is that if xi and xj are same modulo p, then xi plus delta is equal to xj plus delta modulo p for all delta which is greater than or equal to 0. Okay. So now you see that j minus I is suppose equal to L. Okay. So which means that L is the length of the cycle. Okay. So therefore, if you consider these numbers, say xi plus 1 till xj minus 1, so which means that all these numbers are where, are in this particular cycle. So you start from xi, the next number is xi plus 1, the next number is xi plus 2, and so on. So I come till this point, say xj minus 1, and then you come to xi which is equal to xj modulo p. So suppose this particular row is for a prime factor of n. Okay. So therefore, I keep on doing this, and therefore, how many numbers are there in this particular thing? There are, how many elements are there? There are j minus I, that is L. There are L elements, right, in this cycle. So in this cycle there are L elements. So out of them, definitely from L consecutive numbers, there you know that there will be one number which will be a multiple of L, right. So therefore, let that number be say some xi dash, for which xi dash such that I dash is actually a multiple of L. So L is equal to j minus I, right. Correct or not, right. So now so this is the first observation. Therefore, there must be one element whose index is actually a multiple of L, right. So now what the Pollard row algorithm does is like this. So therefore, you know that you have to find out 2 values, right, 2 values for which you will, I mean between which you will calculate the GCD, right. So I mean rather you will take the difference and then compute the GCD with n. So in the Pollard's row algorithm, it progresses like this. What you do is like this, you start from say some xi value, okay, and you start with some next value which is some x dash value. Okay. So you start from 2 values. So therefore, how do you obtain x dash from xi? You compute the fx function. Okay. So okay, you can call it x1 also. So you compute fx1 and you compute the value of x dash. So x dash is nothing but equal to fx. Okay. And what is the modulo? Modulo n. You are computing the original function. Okay. Is it clear? So then what you do is that for the next part, you again take this and you apply one function of fx and you compute the next number. Okay. But for this one, you actually take a bigger loop and you compute 2 fx values. Okay. So therefore, you again obtain 2 new numbers here. Okay. Then what you do is that you again compute one leap here and you get the next number. For the next part, you again apply a bigger loop and you have to obtain 2 numbers. I mean you obtain a number here, a new number here and a new number here. okay, and you keep on doing that. So, what are you doing is that in each iteration you are actually generating two new numbers a and b, right. Why are you doing so? See, what you need to do is you need to detect the cycle, right. So, therefore, that is the main objective. Okay. So, you know that I mean just as a sort of little bit of digression actually, that if I tell you that there is a long linked list, okay, and if I tell you that you have to find out a cycle, so what algorithm will you adopt? So, there is one algorithm very straightforward way which says that you actually release two, say, speed cards through them or two cards through them, okay, one card with a double the speed than the other, then there is bound that both the cards will collide if there is a cycle, right. So, therefore, this is the basis of any cycle finding algorithm. Yeah, whatever, but this is the basic algorithm of a cycle finding algorithm. Okay. So, what you are doing here is, in this case, that you start from xi, you obtain xi plus 1, xi plus 2 and so on, but since you know that there is an I dash which is a multiple of L equal to j minus I, okay. So, you know that what are you doing? You are basically calculating x1, and this is, but this is what? This is the double, I mean each value is a double of the second one. So, therefore, you start with x1, this is say x2, okay. So, this is what? This is x4, this is x8 and so on, right. So, therefore, what you are obtaining is, in one case you are obtaining x2i and in the other case you are obtaining xi, okay. And what is the, so therefore, for this case when you obtain, when you come like when you are computing the incremental function at some place you compute xi dash, right, and you know that I dash is actually a multiple of L, okay. So, when you are computing xi dash, what is the other value that you compute? You compute x2i dash, because there is one point, I mean there is one progression which is like x1, x2 and so on, and the other one which is actually jumping 2 steps, right. So, therefore, you know that these, I mean these two numbers will also collide, because you know that xi plus delta is equal to xj plus delta modulo p, okay. So, what was the starting point? That if xi and xj are same modulo p, okay, then xi plus delta will be also equal to xj plus delta modulo p, right, and j minus I was equal to L. So, therefore, if there is one element which is L times ahead the other element, then they are bound to collide, right. So, you see that j, if I say j minus I is L, then this particular element is L times ahead of this number, correct. So, therefore, this implies that xi dash will also be equal to x2i dash modulo p. Why? Now, because 2i dash is I dash times ahead of I dash, right, and I dash is a multiple of L. Slightly tricky. So, maybe you can just again observe when you go back, but just think on this. That is, what I am saying is this, that is, if xi and xj modulo p are same, then xi plus delta will be congruent to xj plus delta modulo p for any delta greater than or equal to 0. So, therefore, if you know that I dash is actually a multiple of L, then xi dash will be congruent to x2i dash modulo p, because this number or this index is still multiple of L times ahead of this index, right. So, that means these two will collide, and you know that such an element is bound to occur, because if you take L consecutive elements, you will definitely find one such value, right. So, that means such type of, you are bound to get some kind of number which will satisfy this property, okay, right. Though, therefore, the idea is that if you get a collision like this, then you are bound to able to detect this thing. So, but thing is that you are not necessarily finding out the first collision, but you are finding out some collision, okay, and any collision is okay with me. I do not require to calculate this particular point itself. If I find two values which collides in the sequence, then I am done, right. So, what will be my next step? My next step will be to calculate the GCD of x 2 I dash minus x I dash comma n, right, because p will divide x I dash minus x 2 I dash, right, and p will also divide n, right. So, p divides n and p also divides the difference of these two numbers, right. So, therefore, if I compute this GCD and if I get a non trivial factor, then I am successful, right. So, this is the basic working of the Pollard's row algorithm. So, the idea is that if you, now if you see this, that is what it says, that xi plus delta is congruent to xj plus delta modulo p, okay, for all delta which is greater than or equal to 0. So, L equal to j minus I and L is the length of the cycle. So, therefore, now in L consecutive terms like xi plus 1 and so on till xj minus 1, there is one index, say I dash, which is divisible by L, right. If L divides I dash, then this implies that L also divides 2 I dash minus I dash, right. Thus, as I dash is greater than I and 2 I dash minus I dash is a multiple of L, therefore, x of 2 I dash will also be congruent to x I dash modulo p, okay. So, therefore, p will divide x 2 I dash minus x I dash, right, and p also divides n. So, therefore, if I compute the GCD of x 2 I dash minus x I dash and with n, then I should get one non trivial factor of n, right, and if this returns a value like n, then actually it is a failure, because that is a trivial factor. So, what I am looking for is a non trivial factor, right. So, now if so therefore, you see that in this case, this is the previous case, like when this number was 1387, okay. So, what it says that if you just consider these numbers like x3 dash, x4 dash, x5 dash. So, if you just observe this cycle modulo 19, okay. So, maybe it is not so visible, but you can see the dimension of the cycle, like if modulo 19 is a smaller cycle, right. So, therefore, you see that. So, how are the cycles made? You have understood that this is 1387. So, therefore, what we have done is that we have engaged the function fx to find out all these numbers, okay, and all these numbers have been reduced modulo 19 in this particular this part, that is in this row all the numbers are reduced modulo 19, okay. So, therefore, you see that in this case the cycle has got a length of 3. So, what is this? x1, x2, x3, okay. So, you see that x3 is, I mean in this case this 3 is the first number which is divisible by the cycle length, okay. So, therefore, x3 and x6, okay, should also collide, okay. So, therefore, if I compute x6 minus x3 and I take the GCD with 1387, then I should get one non trivial factor, which is indeed the case here. I compute GCD of x6 minus x3 with 1387 and I get 19. So, you see that in order to compute x6 and x3, I do not need 19, because x6 and x3 are computed modulo 1387, okay. So, then what I do is that I compute the difference, okay. So, the one in this case is this number 1186 and the other number is 8, okay. So, therefore, it is 1186 and this number is 8. So, you take the difference and you compute the GCD is 1387, it turns out to be 19, okay. So, therefore, this is how it put together. You can see that you start with one x1 value, you start with another x dash value. So, you see that there is a first starting point x1 and this is the next point which is fx, okay. So, first you compute the GCD of x minus x dash and n, okay. If you get a value of p which is in this case, so therefore, what do you expect here? If you get a value of, I mean which is equal to n, then that means what you have obtained is actually a trivial factor, right. If you have obtained a value of p equal to 1, then you start again this loop. So, what you do is that there is one computation which is fx, again fx, and I mean repeated applications of fx, and this part, like you see that you take x dash, you compute f x and you again compute f x. Okay. So, therefore, these two lines are two applications of the function f x. Okay. So, this is this leap actually here. So, first you start with this point and this point, you enter the while loop, then in one case you start incrementing like this, and the other case you start applying the function f x twice. Okay. So, you come here and again have come here and similarly like that you progress. Okay. Is it clear to you? So, you start with x equal to x 1 here, okay, and this is the x dash value, and the next value what you do is that you compute x equal to f x. So, therefore, you compute x equal to f x means, so therefore, you compute this value of f x here, and in the second case you compute two applications of f x, and inside the loop for the first computation of f x is this. So, therefore, you get these two numbers and you compute the GCD among these two numbers. Okay. So, the main point is that there is one progression which takes like xi and the other progression which takes like x2i. Okay. And then you have seen the rest of the thing, that is if you know that there is an xi and xj which collides, then there is obviously an xi dash which will collide with x2i dash modulo p. Okay. So, I mean, so therefore, I mean you can work out a very simple example which says that 7171 is what we need to factor, and we know that 7171 can be okay. So, therefore, suppose we do not know this factor 71 and 101. Okay. So, you start with some f x value which is f x function which is equal to x square plus 1, and you start with say x 1 equal to 1. Okay. So, x 1 equal to 1. So, therefore, the sequence of xi's begin as follows: you start with 1, you compute the next number is 1 square plus 1, that is 2, then you start with 2 square plus 1 is 5, 5 square plus 1 is 26. What is 26 square? 676, 676 plus 1 is 677. So, till now it is okay, but after that I mean this is also, I mean you see that the next number is 6557, and similarly you compute the numbers. Okay. I have noted an extra number 574 here which because it will be required. So, therefore, if although I do not know the value of 71, let us consider the numbers modulo 71. Okay. So, in this case if I reduce all these elements modulo 71, then you find that these are the numbers. So, you see that these numbers are inside the modulo 71 field, okay, and therefore, you find that there are repetitions, like you find that there are repetitions means that you get a 58 here and a 58 there. Okay. So, there are repetitions. So, you get 1, 2, 5, 26, 38, 25, 58, 28, 4, 17 and so on. So, you get repetitions in this list. Okay. So, the first collision in the above list is x7, okay, x7 mod 71 which is equal to x18 mod 71 which is 58. So, therefore, this is the first collision. Okay. So, you know that I do not know the value of 71, but I am just observing the property. Okay. So, you see that 58 is the first colliding number. Okay. But there are subsequent colliding numbers also, but 58 is the first colliding number, and the idea is that what is the length between this number and this number? It is actually equal to 18 minus 7, that is 11. So, therefore, in this particular list from this point to this point there will be the next one will be x11. Okay. So, therefore, if I apply the Pollard-Rowe algorithm, I may not be able to find out this particular collision, but I will compute x11 at some point of time, right, and the other element will be x22. So, what is x22? x22 is actually equal to 574, okay, and x11 is actually equal to 219. So, there were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. So, x11 is 219, okay, and the corresponding x22 value is 574. So, you take 574, subtract 219 and compute the GCD with 7171, and you will find that the factor is 71. Okay. So, therefore, you see that this gives you a very nice technique, but in this case you are not aware of the value of the factor and you are able to compute the factor. So, what is the runtime of this algorithm now? So, you know that what we have done is that, can you guess the runtime of this algorithm? it will be ordered square root of p, because in each loop you are computing one GCD, right, and what is the maximum length of sequence that you can go, you can start from I and you can continue to j, right, and what value should you keep for j from the birthday paradox, you will keep j equal to O of square root of p, right. So therefore the algorithm can run maximum up to O root p, after that you should be able to get some decision, right. So therefore if you get O square root of p, so what is the order of p itself, it is square root of n. So therefore in terms of n, the complexity is O n to the power of 1 by 4. So therefore this is a significant improvement over the trial division algorithm. Okay. So therefore you have got O n to the power of 1 by 4, which is a significant improvement over the trial division algorithm. Okay. So we will conclude with a very simple technique which is called the Dixon's random squares algorithm. It is a very simple idea which works like this. Okay. So till this part more or less is it clear to us, Pollard p minus 1 factorization and Pollard row algorithm. This is also very quite simple, like suppose, so therefore again there is a supposition here, that is suppose there is a equation like this, x square equal to y square mod n, and suppose the x and y are not same to each other modulo n. Okay. So in that case, okay, so therefore so here actually there will be a plus minus. Okay. So what I am saying is that x square equal to y square modulo n, but two obvious values will be x equal to plus y and x equal to minus y. So excluding them, if I am able to find out two solutions. Okay. So what does it mean? That n divides x square minus y square, so n divides x minus y into x plus y, but neither x minus y nor x plus y is actually divisible by n, right. So what does it mean? That the factors of n are p and q, right. So therefore we can have like x minus y is divisible by p and say x plus y is divisible by q, or the other way around. Okay. So which means that if I compute the GCD of x minus y and n, or the GCD of x plus y and n, I should get non-trivial factors of n, right. But the thing is that I need to find out such pairs. Okay. So you can consider one very simple example like n equal to 77. You see that there are two numbers 10 and 32, for which 10 square and 32 square are same modulo 77. Okay. And neither 10 nor 32 are same, or they are minus of each other. Okay. So therefore if you compute the GCD of 10 plus 32 and 77, then you get 7, which is one of the factors of 77. Okay. So the next thing is that how do I compute this? So therefore I am not really going into the depth of this algorithm, but this is a simple, I think through this example we will get an idea. Okay. And this is the basic of something which we call as the quadratic sieve. So I will not go into that, but this is just an outline. Okay. So therefore you see that suppose I start with n equal to 1829, okay, and you consider the factor base of n equal to, so therefore there is something called a factor base. So the factor base means that if you take, so this is a factor base means basically some consecutive prime numbers. Okay. And all these prime numbers essentially are ensured one thing, that whatever, so this is supposedly a library of prime numbers. Okay. And this is quite a, and this factor base is supposedly a consecutive prime numbers, and which are small numbers. That means I am not considering big numbers. Okay. So the first 10 prime numbers, or first 12 prime numbers, first 20 prime numbers, something like that. Okay. So therefore consider a factor base, and we have included minus 1 for convenience here actually. Okay. So therefore you see that the numbers are 2, 3, 5, 7, 11 and 13. So this is a factor base, and you compute the numbers like square root of kn. So k is an integer, so you start with some numbers like, so therefore you start with like the numbers subsequently will be 42.77, 60.48 and something like that. So there will be decimal numbers. Okay. So if I take integer values which are close to these numbers which are being generated like with square root of kn, then I get, I choose a number say 42, 43, 61, 74, 85 and 86. Okay. So now you consider these following congruences modulo n. So, you see that Z1 square is what 42 square, and 42 square if I take a modulo n, that is modulo 1829, it will actually equal to minus 65. So, now you start factoring minus 65. Okay. So, you see that minus 65 will be factored into minus 1 into 5 into 13. So, here comes the factor base, that is all these factors should actually belong to my prime library. Okay. So, minus 1 belongs to this library, 5 also belongs to this, 13 also belongs to this library or factor base, whatever you say. Okay. Similarly, the next number is 43 square. So, 43 square is 20, which is 2 square into 5. Okay. So, in this case also you find that all these belong to these libraries, right. So, you can continue in this fashion, okay, and you will find that all these numbers are essentially you can factor them using these primes in the factor base. Okay. So, now from these linear congruences or these quadratic congruences you choose some congruences, so that what you can do is that you can represent, see I mean if you say like this, that is I can represent this particular factorization as a tuple of ones and zeros. Okay. So, this tuple of ones and zeros would indicate which prime factor I have chosen, like whether if I have chosen minus 1, I will indicate that by 1. If I have not chosen minus 1, the first number will be 0. Okay. So, in this case, so you see that 2 has not been chosen, so it will be 0 here. Okay. Again 3 has not been chosen, 0, 5 has been chosen, so 1. So, therefore, the right hand side I can represent as a 1 0 vector, right. So, similarly I can represent all these prime factorizations as 1 0 vectors, right. So, now from these quadratic congruences you choose those congruences for which if you add up you get up all 0 vector. Why? Because in that case the right hand side, if I multiply the left hand side, then the right hand side I would be able to express as something square. Okay. And that I can actually apply some Gaussian technique to do that. Okay. So, but I am not really going to those things in depth. So, therefore, if you consider the congruence like 42 into 43 into 61 into 85 square in this particular example, this comes out to 2 into 3 into 5 into 7 into 13 square. So, therefore, you find that you have been able to find out two such numbers which are not equal to each other or not negative of each other, but for whom the squares are equal modulo n. So, that means now if I compute the GCD of 1459 plus 901 with 1829, then I get one of the factors of 1829. Okay. So, this forms the basis of quadratic sieves. So, I have not really gone into this thing, but just as I mentioned, I can just say that the complexity of this will be like this is a sub exponential algorithm. Okay. So, it will be like e to the power of 1 plus O n, okay, and if I remember correctly it will be square root of ln n ln of n. Okay. So, this is I am not going into the proof or anything of that sort, but you see that this is actually a quite efficient algorithm, and this quadratic sieves actually have been followed by something which is probably even more powerful. It is called the number field sieve. Okay. And there is something which is called an elliptic curve sieve also in between. So, all these sieving techniques are actually what are being used in today's present day factoring things, and the projection is that in the year of around 2020, 1024 bit will also get factored. Okay. So, therefore, you need to have higher values of bit security if you are using RSA, maybe 2048 bits. Okay. So, I have followed Douglas Stinson's cryptography theory and practice as a reference, and next day we shall continue with some comments on the security of RSA. So, we shall follow tomorrow on this.